Hi, folks. My name is Chicha Wan, and today I'm presenting Augmenting SUMO with Ring and Barrier Structure Traffic Signal Controller module. And before I get started, I want to acknowledge our sponsor, US DOE Vehicle Technology Office. And in today's presentation, start with background, why we need to do what we are doing here. Then introduce you a little about this so-called NEMA phasing, or which is a ring barrier structured phase definition. Then we talk about two solutions to to introduce SUMO to more folks in the US who can use SUMO for signal timing or signal control. One is to translate the fixed time NEMA timing into SUMO readable timing. Another one is to develop a NEMA phase compliant traffic signal controller module. The traffic signal controller module in SUMO uses a stage-based controller structure. A phase is defined as stage of all allowed movement at the time instance. However, the traffic signal controllers used in North America widely use National Electrical Manufacturer Association phase definition, the so-called NEMA phase definition. The default SUMO traffic signal controller module adds challenges for researchers and practitioners in US to use SUMO for traffic signal related work. So our goal is try to basically enable them to enable the US folks to use SUMO for signal related work. A little bit introduction on NEMA phasing. It has this ring and barrier structure, and phase is defined by the movement. On the right side, this is the typical intersection. You have four legs and have different movement. A phase defines what the movement is, and you can see all the even number phase are through movement, and all the odd number phase are the left turn. And when you have right turn go with the through movement. And you can see it's basically have, if you just look at odd number, it's 2, 4, 6, 8, and then the rest become the even number, 1, 3, 5, 7. The easy way to remember it is a trick we use in the US is so-called 7-11 rule. When you sum the number up on the main street, you have 7. 5 plus 2, you get 7. 6 plus 1, you get 7. And on the side street, you get 11. So it's so-called 7-11 rule. 7-11 is a chain store here in the US. And on the right side, left side is define all the timing, give you the sequence, the duration of each phase, and the yellow or red time. The structure have this 2 ring or could be multiple rings, but here it has 2 rings and 2 barriers. The idea is any 2 phases in one ring cannot happen together. For example, 1 and 2, that will be a through and left turn on the opposing direction. That will be a crash. 1 and 3, it will be basically have a T-bore. And so on. So that's anything on one ring cannot happen together, and anything across the barrier cannot happen together. So 1 and 7, the left turns on different approach, they cannot happen together. Or 2 and 7, same. It goes through here and left turn here. That this will cause some safety concern. And other than that, any combination can happen. You can have 1 and 5, 1 and 6, 2 and 5. So basically 1 and 5, you have two left turn on the opposing direction, and then you can go left turn and the adjacent through movement. A similar idea for a side street. So that's basically the NEMA phasing. And the good part about it is when we do actuated control, for example, there's no vehicle, no traffic for phase one, then it can gap out, can end early. And when phase one end early, phase two start. So you used to have 1-5 to left turn phase, and this one stopped, and then phase two started. And phase five was unimpacted because it's on a different ring. And idea, if phase two stop, it has to wait until phase six stop so that you do not have phases happen together across the barrier. With fixed time control, NEMA timing can be represented by state-based timing. For example, this structure is a ramp. You have side street 3 and 8 come together, and then a 2, when it's not side street, this through movement can always go. Could go with the left turn here or the opposing through. And this can be represented by state-based timing. This one go like that, then 2 and 5, then 2 and 6. And that's finish the cycle. And we can translate that, basically how do we translate them? The way I did was to first list the states for each ring through a cycle. And in SUMO by default, the resolution is 1 second. So I basically list second by second what the phase state will be for each ring separately, ring 1 and ring 2. And this list translate this NEMA timing here. The phase number 1 through 8. And split is the duration of each phase. And then you have yellow and red time. When you use 10 minus 3 minus 1, split minus yellow and red, what you get will be the green time in that phase. So what you can see here is you can see ring 1 start with 3. That usually with 2 and 6 are Main Street phase and they coordinate. So we start from with this one, and then we have phase 3 and it's green, and then phase 3 is yellow, and phase 3 is red for 1 second, and then phase 4. And same for ring 2. Then if we look across them, we can see when the state change for both rings. Basically, we can group them, find just count the duration for each state. This one will be phase 3 and phase 7 green time. And then this is something you're familiar with already. It's the phase definition in SUMO. And you can see it can be actually very complex when you have different combination, especially with the yellow and red time, and combined with different phase of green, yellow, and or red. So you can see start with 3 seconds of green, and then 2 seconds of yellow for this guy, but then the other guy keep going green. So that's basically can give you a translation, and it's actually work well. Well, the translation from NEMA timing to SUMO timing does not perform well under actuated control. As you can see, each phase is kind of here. Each SUMO phase is a state and doesn't care about the ring. So what if we shorten certain SUMO phase? What happened could be you are shorten both ring 1 and ring 2, and as I mentioned earlier, you could have a shorter phase for a certain ring. For example, this phase 1, I do not need that long green time, but then maybe for phase 5, I do need that long green time, and I don't want to cut short for the irrelevant phase. So that's where it does not perform well. And so that's basically the reason why we develop a traffic signal controller model in SUMO. For sake of time, I'm not gonna go through step by step how it's controlled, but I think showing you the input file give you a sense of how. So this input file is still basically same structure, additional file. You have everything in XML format. You have certain value, the detector nav, and detector nav for left turn. This is for actuated control. And it's the typical practice in the US to have stop bar detector, and you know where it is. It's at the stop bar. And the only parameter you want to specify is the nav. And there is the Institute for Transportation Engineer guideline and tell you how long it should be. And usually the through movement will have different nav of detector from the left turn movement. So we have these two parameters. What happened is when SUMO started is read this value and created the detector on each NAND before the intersection, basically those stop bar detectors. And then you tell them the total cycle NAND in seconds. Then what are the phases for each ring? And here you can see it's 4, 1, 2, and then 8, 5, 6. Basically does not have all the 8 phases. It can have whatever shape of your diagram is, and then you tell them the barrier phases, the 4 and 8, and the coordinated phase. The barrier phase are 4 and 8, then coordinated phase 2 and 6. Whether it's in coordinated mode or not, basically if it's in coordinated mode, the cycle length will stay constant. Whenever the previous phase gap out, the time where could go to the coordinated phase, so that is stay a constant cycle length. But if it's not in coordinated mode, it's in free mode, then if you gap out, the time just disappear, and you all the phases can gap out, even the coordinated phase. And then you tell the offset. Whether output state is just whether you were printing out a text file to record what your state was during the simulation, mainly for validation reason. Then the phase definition, you have minimum duration, maximum duration of green. So that when you gap out, you will have star rays. You have to go through the minimum duration, and then you can extend the green whenever there's a vehicle, and you specify how long you extend the green until you hit the maximum duration. And you have yellow, red, and here is the name basically is the phase number, so that we do not need to have a certain sequence for each of the phase. I do not need to go through from 1 through 8. It could be I want to type 8 first, or easier to check the number, which phase it is. One challenge we faced earlier was to figure out what are the turning movement correspond to, or what are the internal links correspond to a certain phase. The way we figure out is to use net edit to change the state string and see which ones are which. So for example, we can find for phase 1 is left turn, and phase 2 you have this one. And when you run the simulation, you may have phase 1 and 5 together. What happens is we combine these two together. It's R until this guy becomes G, and R until this guy becomes G. So that you have phase 1, 5. If certain one become yellow, then that G will become Y. And for this guy, phase 4 here is may have a small g. That's could be permissive phase. Basically, we have 4 and 8. That's a side street. Just to quickly remind you, that's a side street. But then you have the left turn, right? And left turn, you need to wait for a through moment to go. How do we represent that? We just use the small g there.
Hey, I just have to warn you, you have 3 minutes left.
Sure. It's my last slide here.
Okay, great.
Well, besides the conclusion. And then we want to do in-simulation traffic signal timing update, meaning for since now more and more people start to do reinforcement learning and those kind of stuff, and they want to be able to change the timing in real time, or if they do adaptive or responsive signal control, they want to be able to change the timing during a simulation based on the traffic state. So what we did was we update the next cycle timing, and so to let the controller finish the current cycle timing, and then when they start the next cycle, they move all those values from the next cycle timing into the current cycle timing to execute that. And we said that through tracing. There's a set parameter command, and we define a new function, set NEMA timing, and just pass that parameter there. In conclusion, traffic signal controller in the US are operated differently from Europe. We provide 2 solutions for researchers and practitioners in the US to use SUMO for traffic control related work. One is to translate the NEMA timing into SUMO timing. Another one is to develop a NEMA phase compliant traffic signal controller model in SUMO. That's all I have. Any questions?